Alright, so let's go ahead and go over some of the practicalities of using MOSFETs. In the last example, we looked at driving a motor on and off using an N-channel MOSFET. So we have the same circuit over here. This is exactly the same as before. And so, like I mentioned last time, MOSFETs really are ideal for these types of switching applications where you want to turn a motor on and then off. Or you could also, if you were to drive the gate over here on and off fast enough, you could actually vary the speed of the motor. So those are more advanced things you can do once you have like a microcontroller driving the gate of the MOSFET. But in this case, let's just go ahead and look at this simple example over here. And I want to draw attention over to the way the MOSFET is formed in the silicon. So over here we have a conductor for the gate, and over here we have an insulator, right down the center here. And the body of the MOSFET, or the body of the transistor, is also a conductor. Although it's a semiconductor, it's still conductive. So over here we have a conductor. Over here we have an insulator. And over here, again, we have a, I'll go ahead and put this in quotes, semiconductor, but a conductor. Kind of a conductor. Conductive enough. Okay. Now, there's another component that we use that looks like a conductor and an insulator and a conductor, right? So we have a conductor on both sides separated by an insulator. I'll let you think about that for a second. What is it when I have two conductors separated by an insulator? I got a cap. A capacitor is also two conductors separated by an insulator right in the center. Okay? So on the gate of this transistor, inherently to the design of the transistor, we actually have a capacitor that's been formed between the gate and the body. Okay. Now, this kind of is a good thing because this is what gives us that high impedance. So over here, this gate is very high Z. Very high impedance. And as you know, it's nice to have a really high impedance on an input. And this gate of the MOSFET, the way we generally 99.9% of the time we use it, this gate is our input. It's driving the transistor on and off. So having this high impedance, and it's a high impedance because essentially we have a disconnect between the input and the rest of this component, is what gives us that very large resistance, that very large impedance. It means that it draws very little current. Unlike our BJTs, they require some biasing current, right? We need to have some current flowing into a BJT in order to get current flowing, the IC, the collector current flowing through the rest of the transistor. However, in this case, we don't have very much, if any, current flowing in to the device. At least not once the gate is completely charged up. Just to refresh your memory, when you go ahead and apply a voltage, a high voltage, to the input of this MOSFET, you're building up some charge on this plate. But once that charge is built up, the MOSFET is on, and you don't have any current flowing into the gate. So high Z, another way of saying it, very little current enters the device. And that's a good thing. However, it also has a little bit of a drawback. Okay, and to explain this drawback, I go ahead and draw the simplest capacitor circuit ever. Okay, now let's just say initially no charge is on this cap, right? That kind of makes sense. We don't have any current flowing into it. It hasn't built up any charge on it. However, once you go ahead and flip the switch down, we do get charge or current flowing into the device. Once the current flows in, we've developed positive charge on this plate and negative charge on the bottom plate. Now, once the charge is fully developed on there, in other words, once VC is equal to V sub S, once we've fully developed as much charge as we possibly can on the plates of these capacitors, no further current flows into the device. But at time 0, at the very instant that this switch gets closed, this cap, very momentarily, for a brief instant in time, at T0, the current flowing into the device, theoretically, is infinite. It's very, very, very high. Now, a good example of this is, have you ever taken a charger for your laptop or some device, a TV, or pretty much anything that plugs into the wall? And you go ahead and you take your device, let's just say it looks something like this. This is your plug, and you go ahead into your wall outlet, and you go ahead and you plug it in, and all of a sudden you see a spark. What's happening is, inside of your laptop charger or your appliance, you have caps on that power circuit. When we made power supplies, the first thing that we had in that power supply is some big caps, some bulk capacitance, in order to smooth out the ripple. Almost every single appliance has some capacitance between these two prongs on the inside. And when you initially plug it in, especially if you left your charger not plugged into the wall like overnight, right? So that gave it enough time for any charge on the capacitors to dissipate, and then as soon as you went to go plug it in, you saw a spark jump out of the wall a little bit. Well, that's the capacitor with no charge drawing a ton of current initially at plugging in. Now, once the charge has started to develop on there, all of a sudden that resistance starts going up, which leads to less current flowing into the device, and then ultimately you're left at the end of the day with zero current flowing into the capacitor. Okay? Now, that same little issue of drawing a ton of current the moment this switch is closed applies to the gate of the Mosfet, right? Because this essentially is a capacitor. Okay? So what we need to do is we want to provide a little bit of resistance upstream before connecting into the gate so that we can limit the amount of inrush current. Okay? So let me go ahead and draw this. Let's go ahead and say we have our microcontroller and it's driving the input of one of these MOSFETs. In fact, we can go ahead and make it the same exact circuit that we were looking at above. We wanted an 8051 to control a motor. Motors take a lot of current, so we don't want that current to be supplied from the microcontroller, which it couldn't do. And we don't even want to sync that current going into the microcontroller because motors take hundreds of milliamps. So that's definitely way above the syncing ability of a microcontroller to do. So we go ahead and we use a MOSFET in order to do this. However, we're going to throw in a 4.7K ohm resistor or a 10K or even a 100K. It really doesn't matter. Just rule of thumb, I'm going with something in the ballpark of 100K, of 10K or 4.7K. And all we're going to do is limit that initial inrush current. Okay? Now, let me go ahead and write that over here. Resistor limits inrush current. Keyword, inrush current. That is legit terminology for what's going on here. Inrush current is the amount of current that's going to be flowing into this device at time 0 the moment we make this 5 volts or logic level 1, right? When we switch from a 0 to a 1, or when we switch from 0 volts to 5 volts, we're going to have a lot of current at time 0 entering the MOSFET. Now, is it enough to damage the microcontroller? Maybe. But it's not a good practice. So it's always a good idea to put some small amount of resistance entering the gate of the MOSFET, just to limit that inrush current. Okay? So that's kind of the first practicality of using a MOSFET in one of your circuits, which I'm sure you will in 346, 347, 447, 498, 490B. You're going to use a MOSFET for driving most switching things. Okay. So that's the first thing. And you're going to see, if you look up any type of MOSFET circuit online, you're going to see this resistor, and that's kind of the purpose of that. Okay, so let's go ahead and let's get to the next practicality. In fact, I'll start off using this image. Because again, it has to do with having this capacitance on the input to the MOSFET. Okay, now once we've built up charge on this on the gate of the MOSFET, so once we've gone ahead and set this to a high and we have positive charge on the gate, if we were to go ahead and disconnect this for any reason, well, there's nothing to discharge this capacitor. So this circuit is going to remain on. The MOSFET's going to remain on, the MOSFET's going to be saturated, and current is going to be flowing through this motor. So the next thing we want to do on a proper design is ensure a safe operating condition in the case of some disconnection or some failure of the component upstream. So if this microcontroller fails for any reason, or you make an error in your code and all of a sudden your gate is left floating, it's neither a 0 or a 1. One of the things you'll learn about in 346 and 347 is that you have to reconfigure the purpose of the pins of a microcontroller. Now, oftentimes at reset of the microcontroller, initially when the microcontroller gets powered on, sometimes with some microcontrollers, you're not sure of the state of this pin. Before you even start running code, that pin has been reconfigured to some functionality. So we just want to make sure that in the case of any type of disconnection or failure of the component or reconfiguring in software of the component where this pin might be left floating, we want to make sure that we always have the gate either pulled high or pulled low. We never want to leave it floating because that leaves the motor in an undetermined state. We don't know if it's on or off. And we should, because we designed it. So let's go ahead, let's add one more thing to this circuit in order to guarantee good practice and good safe operation of our MOSFET. So I'll draw the same circuit. We put something like a 4.7K to limit the inrush current into our MOSFET. Same circuit as before. And now what we're going to go ahead and add is a pull-down resistor tied to ground. We're going to make this a very, very large value. I guess large compared to the 4.7K. We're going to make this something like 200K. And the purpose of this is so that if you were to get a disconnection over here, all of a sudden this pull down ensures that the charge that was developed on the input to the gate gets discharged to ground. Okay? So if we switch over to green for this, so if we had this on, we have positive charge on the gate. All of a sudden, the microcontroller gets squirrely on us. Or someone ran around and chewed up the wires over here. Whatever happened to leave us in an unknown state, now this charge can be discharged to ground through this 200K. So this is an extra thing that's good practice for safety operation of the MOSFET switching circuit. Now, you might ask, well, didn't we just create a voltage divider here? Absolutely, we did. Now, here's the reason why the 200K is so much larger than the 4.7K. Let's say we were driving this MOSFET on, so we had 5 volts there. And let's see. What's going to be the voltage at the gate, the voltage between the gate and the source? This value is what determines whether the MOSFET is on or off. Now, VGS is no longer simply 5 volts because of this voltage divider that we have here. 4.7K, whose purpose is to limit the inrush current, and the 200K in order to guarantee that if something bad happens here, we discharge and turn off. Well, we go ahead and just calculate using the same equation for a voltage divider. 5 volts times R2, which is 200K, divided by R1 plus R2 equals 4.88 volts. 4.88 volts is still nicely above the gate source threshold voltage. So, we're still turning the MOSFET fully on. And for the MOSFET, we're using the previous example, which had an RDS on of approximately 0.10 ohms to 0.14 ohms. So we're still nicely on. If I were to pick this value too low, then this voltage would not be 5 volts, it would be significantly lower. Okay, so we want to make sure that that doesn't happen when we're adding this protection circuitry in here. So 4.7K, 200K are good values for that. Okay, so that's kind of the second problem that you can run into using a MOSFET. Okay. Now, next up, this actually might be another, well, I think they're all important. This one's really important. Okay, this next one I'm going to go ahead and call problem with thinking the MOSFET is a switch. Okay? Now, it's really easy to fall into this trap, especially when you first start out working with MOSFETs, because they act like a switch. We use them for a switch, so I should think that it's a switch. But it's not the whole story. You see, if you treat the MOSFET like a switch and you just think of it as a switch, you may do something like this. I mean, why not? I got an N-channel MOSFET over here. And the MOSFET's going to behave like a switch, right? As soon as I put 5 volts here. But notice something different about this circuit. This motor's on the bottom side of the MOSFET, right? Instead of being attached to the drain, it's being attached to the source. And you might think to yourself, why not? What difference does it make? Well, here's the problem. For this MOSFET to be on, you have to ask the question, is VGS greater than VGS TH? Is the voltage between the gate and the source greater than the threshold voltage between the gate and the source? Remember, this is the value that tells you the MOSFET is on. Value that determines if MOSFET is on. Okay. So you got to go ahead and ask yourself, is VGS greater than VGS-TH? I mean, I put 5 volts here. But the question is, what is VGS? Well, if you go ahead and we know what the voltage at the gate is, VG equals 5 volts. But what's the voltage at this point? This is VS. Remember, it's not just the voltage on the gate. It's the voltage between the gate and the source that must be greater than the threshold voltage. And for example, let's just say it's 2 volts. Well, think about that for a second. This motor might as well just be a resistor, some load. And if the MOSFET is open, what's the current flowing through this? I equals 0. So if we have no current flowing through this, right? So we're transitioning. We're going from 0 volts to 5 volts. At 0 volts, we're definitely off. We have 0 current going through it. So V sub S is equal to what? 0 volts, right? Well, we have 0 current flowing through it. We have no voltage drop across this. This is just an open switch. Let me redraw that. Let me simplify this a little bit. Right? This is V sub S right there. Clearly equal to 0 volts. So as soon as this hits 5 volts, what's VGS? Well, it looks like it's 5 volts, right? I'm with you on that. I agree. It's 5 volts. VGS is 5 volts. So is 5 volts greater than our 2 volt gate source threshold voltage? Yeah, sure is. Okay. So then what happens? The MOSFET starts conducting, right? So let's go ahead, let's draw this again. Let's draw the MOSFET as it's on. Motor down here. VCC up there. And this is 5 volts. However, this MOSFET, as we already determined, is behaving like it's closed. And this motor just acts like a resistor. So how does this circuit change? Ooh, meant to draw a resistor in there. Alright, so once it's closed, over here is S, the source of the MOSFET. So V sub S is equal to what? Well, it's just equal to VCC. right? Because now we do have current flowing through here. And so we have the voltage drop, the full voltage drop, VCC, across the resistor. So V sub S is no longer 0 as it was when the MOSFET was not conducting. Now that the MOSFET is conducting, V sub S just changed. So if this was, let's just say, 5 volts, now it's 5 volts. Which means VGS is what? Well, it's the voltage between the gate and the source. We have 5 volts on the gate, and we have 5 volts on the source. 5 volts minus 5 volts equals 0. Which means now the MOSFET just turned off because VGS is no longer greater than VGS-TH. Our voltage between the gate and the source just dipped below our threshold voltage. So the MOSFET then goes back to being open. But once it's open, V sub S goes back to 0. The voltage between the gate and the source goes back to 5 volts, which is still greater than our threshold voltage, so then it closes again. But then once it closes, all of a sudden VGS turns back to 0, so it goes back to being open. Well, once it's open, all of a sudden VGS goes back to being 5 volts, and so the MOSFET closes again. You see the problem? We're going to keep on flipping back and forth between open and closed. Just because we put the motor down here as opposed to on top. That makes sense? So that's the problem with treating or thinking of the MOSFET as just being a simple switch depending on what the voltage at the gate is. It's the voltage between the gate and the source that determines whether the MOSFET's going to be on and off. Now, okay. So the simple answer to this is don't do it. Put the motor on the top side. Put the motor on the high side. Have the motor connected to the drain and VCC. So the MOSFET, our N-channel MOSFET, is capable of sinking current through the motor, but we can't have the current being sourced through the MOSFET into the motor. Okay? Now, when you attempt to do this, put the motor on the low side, we actually call this low side switching. As it turns out, an N-channel MOSFET cannot be used for low side switching. So an N-channel MOSFET can only do high side can only do low side switching. And that's where the MOSFET is on the low side of your circuit. If you want to do high side switching, you're going to have to switch to a different type of MOSFET. With a P-channel MOSFET, you can do high side switching. But a P-channel cannot do low side switching. And I think I actually got the low and the high side switching backwards when I said it in the previous slide. So please go back and fix that or change it. N-channel MOSFETs can only do low side switching, where the MOSFET is on the low side. And P-channel MOSFETs can only do high side switching, where the MOSFET's on the high side. Okay. Now, we haven't talked about P-channel MOSFETs. Now, I will say, there are times when you want to do high-side switching. There's times when it's actually necessary to do high-side switching. So, we're going to have to talk about P-channel MOSFET. Now, the concept is essentially the same. The symbol changes. Now, we still have a gate, we still have a source, we still have a drain. All of the terminology stays the same. The only thing that changes is the condition that makes the MOSFET on or off. A P-channel MOSFET is on when the voltage between the gate and the source is less than minus VGS-TH. Just reverses. The voltage between the gate and the source must be less than minus the threshold voltage. So let's go ahead, let's do an example of this. Let's say my MOSFET has a gate source threshold voltage equal to 1 volt. And when it does, the RDS on value is equal to 0.10 ohms. And if I want to make this P-channel MOSFET on, in other words, I want it to behave like a closed switch, instead of driving the gate high to 5 volts to be on, I actually need to pull it down to ground. So now I have the gate tied to 0 volts and the source is tied to my VCC. Let's make that 5 volts. Now, what's VGS in this case? VGS is equal to the voltage on the gate minus the voltage on the source. In this case, 0 volts minus 5 volts, right? Because now our source is the one directly tied to our high voltage, to our VCC. So the voltage between the gate and the source is minus 5 volts. Well, minus 5 volts is equal to VGS, which is less than minus VGS TH, which is equal to minus 1. So minus 5 is much less than minus 1, making our condition true, making our Mosfet on. But notice it's when I tie the gate to 0 volts. If I tied the gate to 5 volts, then we would get 5 volts minus 5 volts, which equals 0 volts, and 0 volts is not less than minus 1. So the Mosfet would be off. Now, let me go ahead and say 5 volts Mosfet off, 0 volts Mosfet on. Now, if you go back to the previous lecture, I said there were a couple of abbreviations for these MOSFETs as far as the schematic symbol is concerned. For an N channel, you can draw an abbreviation like this. For a P channel, same drawing, we just added a little negation bubble on the front. Now that negation bubble makes sense, because the MOSFET for an N channel, 5 volts would make it on, 0 volts makes it off. For a P channel, 5 volts inverted makes it off. 0 volts inverted makes it on. So, these two abbreviations are actually pretty useful. Just make sure you don't fall for the trap of what the source is connected to, because it's always VGS that determines whether the MOSFET is going to be on or off. Now, let me go ahead and grab another sheet over here. Let me show a couple of examples of things we can do with MOSFETs. Oh no, it's 201 in my 311 class. What's going on here? Alright, we're all familiar with the inverter, right? Logic level 0 makes a logic level 1. Logic level 1 makes a logic level 0, right? It gets negated, it gets inverted. That's why we call it an inverter. Well, when we're talking about digital logic, You might have heard of something called CMOS. CMOS is an acronym. Complementary metal oxide semiconductor. Now, as it turns out, all our digital logic, especially our modern day digital logic, what our CPUs are made out of, what our FPGAs are made out of, our microcontrollers, universally across the board, and pretty much all digital logic, is based off of CMOS technology. And CMOS, complementary metal oxide semiconductor. Well, what's a Mosfet? Metal oxide semiconductor field effect transistor. Metal oxide semiconductor. Complementary metal oxide semiconductor. As it turns out, all of our digital logic is actually created using Mosfets. Now, the reason I'm going to go ahead and showcase the inverter is it's probably the first gate you ever learned. And fundamentally, it's the simplest one to create using Mosfets. Let's go ahead and create one. Let's take 5 volts over here. It looks like we're going to use 2 Mosfets. Now, these 2 gates are going to be driven by an input, and the output is going to come from over there. Now, notice over here, this MOSFET's doing low side switching. So, for low side switching, we can only do it using an N-channel MOSFET. The abbreviation for an N-channel MOSFET is right there. So down here, we're going to have an N-channel. Up here, this is going to be high side switching. I'm going to make this a P-channel. And I'm just going to tie the 2 inputs to each other. Now, what happens if I make this 0 volts? Well, remember, let's look at this N channel down here. An N channel with 0 volts tied to the gate should be off. As long as we hooked up the circuit correctly and we're low side switching with it, which we are. So with 0 volts, I expect that MOSFET to behave like an open switch. The P channel, on the other hand, when the P channel gets 0, it's on. Well, look what our new circuit looks like. Go ahead and redraw this. Notice the output over here is connected directly to 5 volts, and ground is essentially disconnected. In other words, we have a pull-up circuit and we have a pull-down at the bottom here. Except in this case, the pull-down's essentially disconnected to the circuit, so our output is merely pulled up to 5 volts. So no surprise, we should get 5 volts on this output. Well, 5 volts is inverted from 0, so Good job, inverter. Let's see if it works in the other case. I wanted to use green. Green's a little more contrasting. All right. So if I put 5 volts over here, notice our N-channel MOSFET is now closed, and our P-channel MOSFET is now open. We'll check out what happens to our output. Our pull-up circuit is open. Our pull-down circuit is now connected. 0 volts on the output. So a 0 gets turned into a 5 volts, and a 5 volt gets turned into a 0 volts, and at no point is our circuit ever, at no point is this MOSFET, or both of these MOSFETs, ever on, or both of these MOSFETs ever off. Now, everything about digital with CMOS technology ends up being complementary. We have a complementary pull up for our pull down. We have a complementary pull down for our pull up. We have one MOSFET to either pull it up and another MOSFET to either pull it down. So this is how an inverter works. In fact, all of our digital logic gates, AND gates, OR gates, NOR gates, NAND gates, XOR gates, trying to think, what other gates? All of our gates are created through some combination of MOSFETs. So if you go ahead and look that up, look up what the internals of an AND gate looks like, you'll see it's going to be about 5. Actually, I don't remember off the top of my head, but a few of these MOSFETs. Okay? So I will go ahead and leave this here, and we will pick up next time. All right, thanks.